Exercise 14b, Adjacency Matrices. A matrix is a grid that stores information. It could be letters, it could be numbers. We can use it to count the number of edges between points in a network, and we will call this an adjacency matrix. So my example here is complete the adjacency matrix on the right. State what determines the number of columns and rows in the numbers in the matrix. So I see that I've got a 0 for an a D with the 1 there, and we've also got an A that has a 1, B has a 2, and E has a 1 there. Now I did say before that we use an adjacency matrix to count the number of edges between points in a network. And by points, of course, I mean nodes or vertices. The fact that at the top there has A, B, C, D, E, and on the right-hand side says A, B, D, C, E, means I can read this like a map. What it's suggesting is that we are trying to count lines from A to A, from A to B, from A to C, and so on. So that first top right or top left corner says from A to A is 0. That means there are no lines, that's because there are no loops at A. Whereas from E to E, that's a 1, because there is a loop from E to E. So we can fill in the numbers accordingly. To fill in the numbers, all I had to do was to count how many different paths there were that connected those particular vertices that have all got the letters in them. So for example, from B to A, there's only 1. From C to A, there's only 1. And from E to A, there's no direct path from E to A, so therefore that's a 0. When you're counting this for the adjacency matrix, you want to make sure to not get confused by degrees, but also not get too confused with paths that are direct and indirect. So yes, E is connected to A indirectly via C or via D, but there are no direct paths. So when we put the numbers into the matrix, we're only putting direct paths. In example 2, we have to draw a network for this adjacency matrix, and I would suggest putting in some letters so you don't get too confused and caught up. So one of the things that I would look at to see if there are any loops, we can see that there is a loop from E to E, which we'll need to put in. And there are also some multiples. So you'll see there we've got a couple of paths that say 2. If we remember from our first example, if there is a vertex that connects to another vertex and it has the numbers 2 or 3, that means there are parallel edges. In the first example, there was parallel edges between B and D. And in this example, example 2, from A to C, there are some parallel edges, and then also from C to A. But let's get drawing. This is a suggested image. There are many different isomorphic versions of this that we could draw. I would challenge you to try to draw this, if possible, without any overlap. I unfortunately fail at that challenge. But here is a suggested way you could draw it. Example 3 asks us to draw the adjacency matrix for this network. We've got A, B, and C. Earlier, I had asked what determines how many columns and rows there are, and what determines it is the number of vertices. So A, B, and C. Each one has a loop on it. And so we can then fill in this adjacency matrix accordingly. For the purposes of networks, we don't need to do any further solving using matrices. That's a separate module altogether. But you are expected to be able to convert from an adjacency matrix to a network and back again.